Question number 1 on the practice quiz for acids and bases is asking what color litmus paper would turn in a specific solution. Litmus paper is an indicator, so we're going to definitely need table M. But before we can decide what table M would give us, we need to know what CH3COOH is. And if you recall from back when we did organic chemistry, this is the functional group for organic acids. But also, if you look in this table here, table K, you're going to see that CH3COOH is one of our common acids. So even if you didn't recall that, table K or L, if it's a base, is really going to help you with that. So this is going to be an acid, which means that its pH is going to be relatively low. Whenever they ask this, go ahead and assume the extreme end of whatever end of the pH scale that we're talking about. So since this is an acid, we're going to assume that it's all the way down to a pH of about 1. So looking at the acid-base indicator table, table M, here's litmus, and it goes from red to blue in 4.5 to 8.3, meaning in the low end of the scale, before it gets to 4.5, it is red. So I am going to put red for my answer, and my reasoning is it's an acid. The next question asks if MgCrO4 is an electrolyte. Electrolytes are acids, bases, and soluble salts. So we can start by looking in our acid table, and I do not see anywhere in here MgCrO4, so it's probably not an acid. That list is not all-inclusive. And then when we look at table L with our bases, MgCrO4 isn't there either. But it could be a soluble salt. So this is reaching back a bit, but table F is where you're going to decide if something is soluble or not. So we look it up based on the negative half of the compound, or the CrO4, and you're going to find that over here where it says insoluble. So usually chromates are insoluble, but depending on what they're bonded to, or the first half of the compound there, the magnesium, they may be an exception and they will dissolve. And sure enough, here's magnesium. It is an exception, so when magnesium is bonded to chromate, it's actually soluble. So that would be an electrolyte. So we're going to say yes, and our reason is that it is a soluble salt. Electrolytes are acids, bases, and soluble salts. Next question is, will magnesium metal react spontaneously in KOH? So we said previously in the notes that most metals, all those except for the ones below H2 in table J, which are copper, silver, and gold, will react spontaneously in acids. This here, not an acid. And if you need confirmation of that, you will actually find it in the common bases table. It is right here, KOH. It's actually one of our stronger bases. So this is going to be a no, and our reasoning would be that KOH is a base. Most metals react in acids. Next one, is H2CO3 considered an electrolyte? Electrolytes are acids, bases, and soluble salts. So starting with our acids, we can look for H2CO3, and usually the ones that start with H are going to be acids anyway. And here it is, H2CO3, or carbonic acid. So we're going to say yes, and to justify it, it's an acid. Next one, we have MgCO3. Doesn't really look like an acid. Most of our acids actually start with an H. Doesn't really look like a base, although not all of our bases have an OH in them. when we check our list. NH3 doesn't have OH in it, but it's not one of those, so it may be a soluble salt again. So I'm going to pull out my table F, and we're looking for CO3. Here's CO3, or carbonate. And it is usually insoluble, but we'll see, except when combined with a group 1 or ammonium. Magnesium, if you look in the periodic table, is a group 2. So that is not an exception, so it will not dissolve. So I'm going to say no, and to justify that, I'm going to say it's not soluble. Next question, what color is phenolphthalein in HCl? So color, we're going to look in table M. So I'll pull out table M again. But also you need to know what HCl is. Hopefully by now you do. We've used it so often in lab. It's an acid. So we're going to assume the extreme end of the acidic end of the pH scale, or a pH of 1. And when you look at phenolphthalein, it is colorless until a pH of about 8. So it is going to be colorless. And we'll just say it's an acid. Next one, will copper metal react spontaneously in H2S? Might be helpful to have one more table here, so I'm going to pull out table J. So here's table J. It's been a while since we've really looked at this, but table J, all of these metals up to where H2 is will react in an acid. And H2S is an acid. You could confirm that by looking in this table. No, you can't. H2S is an acid, and you can kind of assume that since it starts with H. And copper is not above H2. It's actually below H2. Copper, silver, and gold don't react in acids. So we're going to say no, and to justify that, we're going to say that it's below H2. Move this out of the way. In table J. So those metals that are below H2 in table J do not react in acids, and none of them really react in bases either. All right, next question is referring to this reaction here, which even if you hadn't covered neutralization reactions, you would know it's a double replacement reaction. So we can figure out the products of that reaction. The H is going to end up with the OH, which happens to be water. I like to write it like that when we're dealing with neutralization. And then the BA is going to end up with the SO3. And then we need to look up their oxidation numbers. Barium is a group 2, so it's a +2. And SO3 being a polyatomic ion, you should look up in table E, and it's -2. So since those oxidation numbers cancel each other out, we don't need any subscripts. So of the two products of this reaction, we have water and we have an ionic compound, which is a salt. So when they ask what salt will form, we're going to say BaSO3. And you can just say double replacement to justify how you came up with that particular salt. Next question, which reactant is an Arrhenius acid? If you recall, Arrhenius acids make H pluses in solution, and pretty much any acid is going to be an Arrhenius acid. So you're going to pick the acid from your two reactants. This is the acid, usually starts with an H plus, and then this is our base, usually has an OH in it. So we're going to say it's H2SO3. And I'm going to justify that by making sure I point out it's Arrhenius by saying it makes H pluses in solution. So when you justify that one, you've got to justify it by using the definition of an Arrhenius acid. Number 10, why is this reaction called a neutralization reaction? The products are neutral. or you could say that the acid and the base neutralize each other. And then to justify that, you can say water and salt are neutral. Next question is actually a titration question. So if we have 35 milliliters of 2.40 molar NaOH, so these are the volume and molarity of the base. They want to know what molarity of acid would completely be neutralized by 25 milliliters. So using the titration equation from the back of your reference tables, we don't know the molarity of our acid, so we're looking for that. The volume of our acid was 25 milliliters. The molarity of our base is 2.40 molar, and the volume of that base was 35.0 milliliters. So we'll divide by 25 milliliters. And then these cancel out, and all we have to do is multiply and then divide by 25. And when you do, you get 3.36 molar. Another titration question. So again, we're going to be using MAVA is equal to MBVB. This time we have the molarity of our acid, and we have the volume of our base and the molarity of our base. So we're going to be looking for the volume of acid required to neutralize that base. So we're going to plug in our numbers. We have 4.00 molar for our acid. We're looking for the volume of the acid. Our base is 8.00 molar, and the volume of that base is 25 milliliters. We divide by 4. And the answer we get is 50 milliliters. And that makes sense. Since the molarity of the base is twice as strong as that of the acid, you would need twice the volume to neutralize it. All right, next few questions. Is solution A acidic, basic, or neutral? We're going to say acidic, because the pH is less than 7. Next one, what is the OH minus concentration of solution C? So we discussed the whole log of, or negative log of the concentration of H plus solution being the pH number. So the pH is actually the concentration of H pluses for each of these, and that is the negative exponent on that concentration. And then the concentration of the OH minus would have to, when you add the exponents, they have to total 14. So this one would be 1 times 10 to the negative 11, 1 times 10 to the negative 8. That was too small. 1 times 10 to the negative 5. So for number 14, the OH plus concentration is 1 times 10 to the negative 5 molar. And our explanation can just be that the H plus concentration is 1 times 10 to the negative 9. And then number 15, what is the H plus or H3O plus ion concentration of solution B? We already figured that out to be 1 times 10 to the negative 6 molar. And that we can justify because the pH is 6. 16 is solution C, acidic, basic, or neutral. I'll leave that so I can still see that. It's going to be basic. And this time it's really specific about how we're going to justify this. We have to do it quantitatively, which means with numbers. using the H plus and OH minus concentrations. I've already figured those numbers out, so I can just write them in. For the H plus concentration, it is, that's supposed to be an H, 1 times 10 to the negative 9, which is much smaller number than the OH minus concentration, which happens to be 1 times 10 to the negative 5. So you'll need to figure out those concentrations and then use them in order to write an expression like I did. Number 17, how many more times acidic or basic or alkaline is solution A compared to solution B? The difference between these two numbers is actually a difference in place value. It's not just a difference of 3, but it's a difference of 10 to the third. So it's actually 1,000 times different. So it's 1,000 times different. And to justify that, you could say that the pH value, 6 minus 3, is equal to 3, or 10 to the third. What color would bromothiamyl blue be in solution C? So we need table M. Solution C has a pH of 9, so in bromothiamyl blue, a pH of 9 is above this end point in the change, so it'll be blue. And to justify that, we can say that the pH is greater than 7.6, which was the top end of that scale. If a strong base were added to solution A starts out with a pH of 3. What color would methyl orange turn? So as we add a base, the number is going to continue to increase. So it's going to start at, let's see, at a pH of 3, it would start out red, and then it would turn orange, and if you kept adding it, it would end up yellow. So we're going to say from red to orange to yellow, and we can justify that by saying that the pH will increase. And then letter D solution being 1,000 times more basic, so that means that the pH is going to go up by 3. So let's look back. Solution D, more basic than B. So here's B. It had a pH of 6. So if it's going up by 3, it'll be 9. And you can justify that by saying the pH would increase by 3. And that's it.